but I've had a lot of waters have been under the bridge physically for me since then, so I'm not going to walk around the stage here. I'm going to sit here a little bit, hopefully do a little. What I'm going to talk about tonight is how to do some real science, which is what it's all about for me. I mean, I love observing, I love photography, but doing some science and figuring out how other people did science, in this case, is sort of what it's all about for me. Now, this is my observatory group near a little town called Bethune, South Carolina. And you can see the Milky Way is very prominent from there. This is a very dark sky site within our state. And the question that I always ask, you notice how you can see the core is bright. You can see that it extends out in both directions, but it's covered up in dark dust clouds. And really all you can see is just the area that's right around where we are. And so the question is, how did astronomers get from seeing the Milky Way as we see it to an accurate model of it being as a disk with even arms mapped out and lots and lots of detail? And so this is where the story is going to be. And also, excuse me, of course. I wondered how they figured out what the diameter of it is, or how many millions of years it takes the sun to go around it. All of this stuff comes out of the story I'm getting ready to tell you, and it turns out that you can actually build some equipment for very little money and figure all this out yourself. And my goal with this project was to replicate the science that was done back in the 1950s and early 60s when we went from that to that. This is my observatory, the telescope room anyway. It's got also a warm room and a bathroom and a kitchen and everything. This is the telescope room, and most of you probably know me as an astrophotographer. But I also do a lot of other stuff as well. I'm also a photographer down at Cape Canaveral, with the Space Force down there, Kennedy Space Center. I do up-close photography with rocket launches, and that's something I want to get back into shortly. But my background and what I spent my career in doing is radio frequency engineering. I was the chief engineer for the South Carolina Educational Television Network, and I designed and built television stations, radio stations, satellite facilities, microwave facilities. And so I've got a pretty good background in radio frequency technology, and that's something that I'm really interested in. So it was sort of a natural thing to put my love for astronomy and for radio frequency engineering together. Now here is a spectrum of the electromagnetic, diagram of the electromagnetic spectrum. Now we all have a passion for observational astronomy, and some of us for astrophotography, but realize that all that we see within our hobby is just in that very little tiny window there in the middle called visible light. So it would be like we're missing out on so much that's out there in the universe. It'd be like listening to a symphony orchestra as played through an old telephone with a very limited frequency response. We don't hear the highs or the lows. We only hear just a little bit. So using optical wavelengths only, we really only see a tiny fraction of the information that's out there. And this chart shows from lowest to highest frequency, or longest to shortest wavelength, where we go through the lower parts of the spectrum, the infrared range where James Webb works, up through visible light and on into X-rays and gamma rays. But down at the bottom, there's a lot of range that's in the radio frequency spectrum. And this is the problem. We live at the bottom of an ocean of the air, and the air contains water in the way of humidity and clouds, as we obviously can see, along with particles of dust, like the dust of the smoke from Canada. And so it makes it anything but truly transparent to optical light. But you can see that at visible wavelengths here, where the red, green, and blue parts of the visible spectrum here, It's fairly transparent, not completely transparent, but in the very short wavelengths up here about X-rays and gamma rays and things like that, it's opaque as it can be. It might as well be a brick wall. Same thing down here where some of the microwave frequencies are. That's why the microwave satellites are in orbit. But there's a big opening here in the radio frequency part of the spectrum where the air is virtually clear. Rain doesn't matter, clouds don't matter, day and night doesn't matter. And so we're not at the mercy of the weather to make observations. We can make observations 24 hours a day, 365 days a year. So some of the advantages is that we're not at the of radio astronomy is that we're not at the mercy of the weather. We're not really at the mercy of day or night. I can do observations in the middle of the day just as well as at night. And I can detect hydrogen, which is the most, and this is what this project is all about, which is the most abundant element in the universe. So you're able to see a lot of information in the radio spectrum. Turns out hydrogen, and we'll talk about how it does this in a minute, it gives off a frequency of 1420 point some odd megahertz, which is a wavelength of about 21 centimeters. And we'll look at the physics of that in just a minute. So basically with a radio telescope, we now have access to 90% of the universe that, if you were only looking at light, you wouldn't see all of it. Yeah, and so dust really doesn't absorb it as well either because the wavelength is so long compared to light. I mean, with light, we're looking at wavelengths on the order of microns. And radio waves, in particular hydrogen, we're looking at a wavelength of 21 centimeters. So that's very, very much longer than the diameter of a dust particle, and so it goes right through with no problem. Now, it has some disadvantages. One is resolution. Since the wavelength is so long compared to visual wavelengths, it takes a much, much bigger receptacle or antenna than it does a telescope to see detail in visual observations. Because it all has to do with the ratio of the wavelength that you're detecting to the size of the antenna itself. And trying to make a picture out of the data is very, very complex and it takes a lot of computer time and things like that, but I'm not going there in this project. But if you think about the first picture of a black hole that was released a few years ago, that was taken by radio telescopes scattered all over the Earth using something called interferometry, which we'll talk a little bit about. But even so, it was not a very detailed picture. Okay, again, getting back to the wavelength versus the size of the antenna. This is why radio telescopes are so darn big. The one on the upper left there is the one in West Virginia, in Greenback, West Virginia. It's a couple of football, well, it's like a football field in diameter. At the upper right is Arecibo that collapsed back a couple of years ago. And then down below is the very large array. And it's set up with multiple antennas to do interferometry, as we'll talk about later, but they're all big. So the history of radio astronomy pretty closely follows the development of radio through the 20th century. In the early 30s, Bell Labs was building a cross-country radio communication system. And what they found was that they had a low level of noise that came up periodically that they could not figure out where it was coming from and what was causing it. And it turns out that every system across the United States experienced the same thing at virtually the same time. So they got hold of an engineer on their staff. His name was Carl Jansky. And they tasked him with solving the problem, or at least finding the problem and hopefully finding a fix for it. And what he found was it appeared once every day, but not exactly 24 hours separated. He was seeing the noise separated about 24 hours and 4 minutes. And if you think about it, that's sidereal time. So he knew that it was coming from the sky, and since it was coming from due south, he figured it was coming from the center of our Milky Way. But Bell Labs, he really wanted to follow up on this because he thought that was fascinating. But Bell Labs wasn't interested in following it up and investing any more money because the problem had been found and there was nothing that they could do about it. It was coming from outside. So Jansky never was able to follow up on it, but we do tribute to him in that the basic unit of signal strength in radio astronomy is now called the Jansky. There was a number of amateur radio operators during that time as well in the 1940s and around World War II, plus a number of engineers. Think about what was happening back then. We were developing radar. World War II was really driving the invention of radio communications and, or at least the techniques of it. At the same time, quantum physics was being developed at the same period, which ended in the atomic bomb that ended World War II. So the physics of atoms and radiation and how they all worked was becoming pretty common knowledge. And as the war ended, a lot of these engineers were out of work. So they started looking for other technical fields that were similar, and they moved into industry and academics. But one of these fields that appealed to a lot of them was the new field of radio astronomy. In the 1950s, a lot of they started building very large radio telescopes around the country. This one is in Ohio. It's known as the Big Ear. It was built in 1965 at the University of Ohio. And it's basically the size of a football field. If you look at the far left over here on the left side, there is a tiltable reflector that could be tilted at different angles to basically control the elevation of the signal that was coming in, and it bounced that signal to a parabolic reflector on the right side of the field, and that bounced back to this device here that was on train tracks that could run back and forth horizontally. And so you had a somewhat steerable large antenna. This did a lot of good research back in the 60s, and it was finally turned over to the SETI program in the mid-70s, and this is the antenna where the so-called wow signal was picked up back in the late 70s. That they thought was little green in, but it turned out to be two interacting comets. So, but it was very useful. Other big antennas for large telescopes that had much higher spatial resolution were Arecibo, that was built down in Puerto Rico, and other telescopes like the new one in China called the FAST telescope, which is even bigger. Unfortunately, Arecibo is no longer with us. It collapsed. The reasons are arguable. But anyway, so there's lots of work going on with very large telescopes because that's really the only way you can get spatial resolution. Now, the importance of radio astronomy in science is borne out by the fact that governments around the world have agreed to protect certain frequency ranges radiated by a number of astronomical objects and substances. And so they will not license or allow any terrestrial transmitters in these ranges just to keep down the local interference. So these are just a short list, it goes on and on actually, of the protected radio spectrum segments. And I've got the top one, or the second one from the top highlighted. That is the frequency of 1420.406 megahertz at a wavelength of 21 centimeters. That's going to be really important to the story I'm going to tell. Now, the study of how atoms work was big science in the 1940s. The nuclear model of an atom made of a positive core of protons surrounded by orbiting negative electrons that was proposed by Ernest Rutherford in 1911 and further refined by Niels Bohr in 1916, was being radically modified in the late 20s by the new science known as quantum mechanics. And everyone, even Albert Einstein, was working in this new field that provided a very different look at these particles. And one of the guys that was doing a lot of work was a guy named Hendrik van der Hulst, and he was a physics student, and what he was studying was how the protons, or the proton, in hydrogen's case, only a single proton, how it rotates in relation to how the electrons in orbit around it rotate. And what he found was that, in general, they have a parallel axis of rotation, and they both rotate in the same direction. Now, what he theorized was that once every 10 million years for a single atom, that we have something called a microfine energy transition, where the electron actually flips its spin axis over. And what happens there is that the total energy in the system is slightly less than when they're parallel, and so to balance everything, it has to give off a photon of energy, and that photon is calculated to be at that frequency I gave you, 1.402 or 1420 megahertz with a 21 centimeter wavelength. And you would think, well, once every 10 million years in a single atom, giving off just one photon, you wouldn't be able to detect much. But think about this. If you had 1 million atoms in a jar, it would be expected to give off one 21 centimeter photon every 10 years. If we had 10 million atoms, that would happen once a year. If we had 1 billion atoms, that would give off a photon every 3.5 days. And of course, 1 billion atoms doesn't fit on the head of your fingernail here. And so think about the hydrogen clouds in our galaxy that are hundreds of light years across, in some cases thousands of light years across. That's a huge volume of hydrogen. And so all of those going off at one every 10 million years is basically a continuous signal. And you can pick it up with a very sensitive receiver, and you can even pick it up with a homemade receiver that I'm going to show you here in a few minutes. Now, not all hydrogen atoms go through this hyperfine transition. It can only occur where an atom has both the proton and the electron still intact. Inside of real high energy processes like inside of stars, the electrons are stripped off, they're ionized, and so you don't have the foundation basically to make that radiation. And so the only types of hydrogen clouds that can do this are the clouds that basically are away from stars, or that are fairly good ways away from stars. But really, there's a lot of mechanics of how radiation can originate, and one of them is called black body radiation. It basically says that everything that is above 0 degrees, absolute zero, radiates photons in accordance with their temperature, and the wavelength is according to their temperature. Now, even you do this. With your body temperature of 98.6 degrees, you radiate energy with a very short wavelength of 9.3 micrometers. Now, where is that in the spectrum? It's in the infrared spectrum. That's why your body is warm, and you can be seen on an infrared camera, because your mass is giving off radiation, black body radiation, as everything else. So, Van der Hulst had predicted that we would see 21 centimeter radiation coming from giant hydrogen clouds, but it was theory only at that time. And so a couple of physicists named Harold Ewan and Edward Purcell at Harvard University in 1951 built a couple of antennas and started looking for it, and sure enough, right away they found it. And this antenna on the right is basically a horn antenna, and it's now on display at the National Radio Observatory in Green Bank, West Virginia. Now, this is my first attempt. This was about 1.5 years ago. I found an old Wi-Fi dish antenna about 1 meter across. And I thought, well, let me see if I can pick up anything with this, not even realizing that I had enough capture area there to do anything. But it's calculated to have a beam width of 14 degrees at this frequency with 1420 megahertz, which means that you're looking at a single pixel that's about like that. So the resolution is terrible, obviously. You need big antennas for high resolution. But with this little antenna, I was able to pick up the hydrogen line, what's called the hydrogen line, as the Milky Way crossed in front of it. You see, I had them mounted on a tripod outside my workshop. And I would aim due south at the meridian, and then watch as the Milky Way crossed in front of it. And as the Milky Way crossed in front of it, you see the spectrum analyzer come up with the signal at 1420, and you see that signal move up and down the frequency due to Doppler's. And I'll show you that in more detail in a few minutes. But that got me hooked right there, the fact that you detect this with such a small device. Now this is the feed horn I made for it. Obviously it was designed for Wi-Fi. Wi-Fi is at 2500 megahertz. So I had to tune it down to 1420 megahertz. So I took the antenna out of the feed box and built another antenna that was of the proper length. And this device right here is a low noise amplifier. You have to put a low noise amplifier to get some gain right near the antenna so that you don't lose all of your cable going to your receiver. And this is the completed feed horn here. What you'll notice, what is this? That's a compact disc. Turns out that a compact disc is a perfect diameter to act as a reflector for 21 centimeter energy. And so this is the pickup antenna inside this little black box here. And a quarter wavelength back, I put this reflector, and what that does is it keeps energy coming in directly in that doesn't bounce off of the dish itself and come back to this pickup. It keeps it from picking that up, which would be out of phase. But also, any energy that comes in bounces off the dish and goes back here that overshoots, it gets bounced back again and you pick it up. So it makes it a little more efficient. But again, this is made out of an old compact disc out of my closet. This is a schematic of the receiver as it sat. Just a modified Wi-Fi antenna here. This is the low noise amplifier that had about 40 decibels of gain, and I'll talk about what a decibel is in a minute, but 40 decibels is basically about a 10,000 amplification. It's multiplying power coming into it by 10,000 times, followed by another 40 dB amplifier. So what is 10,000 times 10,000? That's a lot of gain, and then it's fed into, by the way, these are available on Amazon for about 39 bucks. The SDR here, the software-defined receiver, again, is on Amazon for about $40. And then I was using my laptop with some free software called SDR Sharp, and I used Stellarium to find out what the Milky Way is coming in front of the antenna. So the total cost here was probably maybe about $120, something like that. And I was able to pick up the hydrogen and the galaxy. Now, let me move this so I can see my notes here a little bit. Anyway, in general communications, and especially in radio astronomy, the most important issue is signal-to-noise ratio. What we've got to do, there's a lot of noise there, and we've got to find a very, very weak signal buried down in the noise. And so noise is defined as random unwanted signal, and it's always present in any system that's at a temperature above absolute zero. So in a high-performance receiver system, the noise figure, or how much the receiver itself contributes to the noise, is determined by the first gain stage. That's why it needs to be a low noise amplifier. What the amount of noise that's contributed by the amplifiers after that really doesn't matter that much. We're less concerned about the absolute signal level than with the ratio of the power compared to the noise. And that's measured in decibels. And basically a decibel is 10 times the log of one power compared to another power. And we can use these as ratios. 10 dB is a power ratio of about 10. 20 dB is a power ratio of about 100. 30 dB is about, so that 40 dB amplifier has got a gain of about 10,000. And I'll tell you this just because there is some calculations involved here. But anyway, in radio astronomy, the signal levels are measured in Janskys, named after Carl Jansky. And a Jansky is an extremely, very small unit of energy here. It's 10 to the minus 26, with 26 zeros in front of zero, watts per meter squared per hertz. Don't worry about what all that means. It's just a darn small measure of think about it, let's see if I can get this to work. Basically, radio astronomy signals are extremely weak. How many of you in here have radio operators? A few? Okay. Your basic mobile radio has a sensitivity somewhere around about 110 dB below 1 milliwatt. A Jansky is nearly 100 dB or 10 billion times lower than that. So that's the kind of sensitivity we've got to have. And you can do that even with off-the-shelf components. The signal levels that we're looking at, a quiet sun at the hydrogen frequency, it gives off somewhere around about 500 million Janskys. And the strongest Milky Way sources are about 2,000 Janskys. So I know that I'm seeing them, so that means that my sensitivity is lower than 2,000 Janskys. And here's some typical antennas. I'm trying to get my notes to get out here. That amateurs use. If you've got an old satellite dish, they work great. And you can probably find those for free. You just need to make a feed horn for it that corresponds to the proper frequency. These are dishes that are made out of, horns that are made out of construction material. This right here basically is the siding on a house. The styrofoam siding that has aluminum foil on one side. It makes a dandy antenna for very little money. Now, I've upgraded since my little one out in the garden. This is my current antenna. It's a 1.8 meter antenna that I built out of a discarded, what's called an ITFS antenna, instructional television fixed service. Basically a big Wi-Fi antenna at 2.5 gigahertz. And I built the feed horn up here, and I built the structure for it there. All the electronics are up in here, and it goes to the receiver, which is in the building, which is at my observatory. This is about an hour from my house, and I can operate it remotely from home. Poured a nice concrete pad to make it stable. Right now, it does not have motors on the axes, and that's one of the future projects I've got. I can go out to the site and aim it however I need to for the study I'm working on at the time, and then I can actually do the study from home. This is some details of how it was built. This is the feed horn over here, which is built out of a 6-inch stovepipe. Turns out 6-inch stovepipe is exactly the right diameter to make a waveguide for 21 centimeters. And again, here is the antenna itself. I built this frame back here to allow it to tilt. This shows the feed horn and the electronics in the waterproof box back here. And it's focused right at the right focus length for this antenna. Here is some of the electronics on my workbench, and here's the electronics that are in that box right there. These are two amplifiers. One of them is a low noise amplifier, and what's called a DC block that allows you to pass DC power through the cable out to the antenna. Now let's look at a little bit about the geometry or the geography of our galaxy. We need to, and this will come back when we start looking at the measurements themselves. If we look from the top of our galaxy, which top in space is sort of relative. But anyway, here's the sun about half the way out from the center part of the galaxy out to the edge. And this part over here is called quadrant 1. This is basically what we see from the northern hemisphere. Remember, Scorpio would be somewhere in this red region here where you're looking at the brightest part of the galaxy towards the south. And the further east you go, at 90 degrees from the center of the galaxy, it would be here. This area down here is quadrant 2, quadrant 3, and quadrant 4. And from the northern hemisphere, we really see very little of quadrant 4, if at all. We can see a good bit of, well, we see all of 2 and a good bit of 3, and maybe occasionally a little bit of 4. Depending on the seasons, but so everything that I'm measuring is up at these quadrants right here. Now, there's a coordinate system, just like on Earth, where we have latitude, longitude. There's a galactic coordinate system as well. And from where we sit, where the sun is, If we point directly towards the center of the galaxy, that is 0 degrees longitude. And then as we move eastward, out along the plane of the galaxy, we get higher and higher in longitude until when we're looking at our back, basically 180 degrees, way down to 180 degrees longitude. Now, the galactic equator, it's a flat disk, or close to being a flat disk. The axis of the disk is at 0 degrees latitude. And if you go north of here, that's positive latitudes and negative latitudes down below. But everything I've done with this project has been right on the equator at 0 degree latitude. But bear in mind that when I'm talking about 0 degrees longitude, I'm talking about looking directly at the center of the galaxy. And as we go up in longitude, I'm moving eastward. Now, this is obviously not to scale, but it shows you that in the summertime, when we're on the nighttime side of the Earth, we're looking towards the center of the galaxy. That's why we can see Scorpius and Ophiuchus, and not Ophiuchus, but all the Teapot and all those places down towards the south, because they're right near the center of the galaxy. Now, 12 hours later, or a season later, basically, in the winter, 6 months later, the nighttime sky is pointed out this way. And so we see just a little of this outer area of the galaxy. That's why the winter Milky Way is so dim. It goes down below the side of Orion. You probably see it on really, really dark nights. This gives you an idea when you look at the Milky Way. As we're looking along its axis, that's 0 degrees longitude. That's the longitudinal axis, and then either above it or below it is latitude. But we're not really dealing with that right now. Here's a good picture, sort of a panorama showing the center of the galaxy here at longitude of 0. And as you go east, there's 60 degrees longitude, 120 degrees, and it comes back around itself over here. And this area over here is in quadrant 4, so we don't ever see it from the northern hemisphere. But also look at what you're seeing here. There's a lot of dust there, and it's blocking everything beyond that. And even looking at this picture, could you tell that we live in a spiral? It'd be very tough to do that. Now, we do have some clues. We can look at other galaxies. We've got Andromeda right next door, and it's flat with a bright center, and we see that it is obviously a spiral. So they had good clues that we live in a spiral as well, but the measurements I'm going to show you how to do is what sealed the fate of that. Now this is a radio map of the galaxy, taken at 408 megahertz here. And you can see the large and small Magellanic clouds. You can see the brightness along the bar of the galaxy here, along the 0 degree latitude area. We see some big swaths of radio emissions going above and below the galaxy. You can see some hot spots here in Cygnus. There's another one over here in Bella, which we can't see from here. And all these sorts of things. So the radio sky is very different than the visible sky. Now, how do we, what we're getting out of the receiver? This is basically the display of a spectrum analyzer, and very simplified. The frequency is along the x-axis, going from low frequency to high frequency. Amplitude of the signal is along the y-axis, going from low amplitude to high amplitude. Now, this line in the middle, I've got drawn 1420.406 megahertz. That's what a hydrogen signal, a pure hydrogen signal, would look like. It's just a single line with no width to it, no bandwidth to it. However, what happens is, and what we actually measure is this. This is a Gaussian frequency distribution around both sides of 1420.406 megahertz. And what causes that is that we're looking at a hydrogen cloud, and a cloud has random movements within it. There are atoms that are coming towards us, there are atoms going away from us, and so you have Doppler shift to worry about. The atoms that are coming towards us are shifted
higher in frequency, up this way, and the atoms that are moving away from us are shifted lower in frequency this way. So the fact that we see this shape means that we're looking at a cloud that has internal motion in it. And we can kind of figure out how fast all these things are traveling by the width of this Gaussian frequency distribution. Now, what we also measure is, here's the reference frequency right here. But we might see a cloud that's moved off in frequency. In this case, it's moved lower in frequency, and if we can measure the change in frequency here, we can plug it into this equation and find out what the Doppler shift is, and how fast it's moving. So just from looking at the shape of the spectrum and where it is in relation to the reference frequency, we can tell how fast that cloud is either moving towards us or away from us. And we've settled on this standard notation, is that positive velocities, in other words, the object is going away from us, it's receding from us, is called redshift, because in light it would be shifted towards the red end of the spectrum, the longer wavelength. Negative velocity is approaching us, something's coming towards us or us coming towards it. And that's called blue shifted because in visible light it would be shifted to the blue. This is exactly what we're talking about with redshift of galaxies as the universe expands. So there's a lot of other motion going on too. Our sun is moving, is bouncing around around the galaxy. Its motion is being pulled around by the mass of Jupiter. It pulls it out of a perfect path. We have the Earth going around the sun. We have the moon going around. The Earth going around the sun. The moon going around the Earth. And if we're going to measure the speed of something else in the galaxy, we need to determine, or we need to find a standard of reference or a standard of rest. And it turns out by using just us or the sun, that's a lousy way of doing it because we're bouncing all around globally. So what has been determined is that the local group of stars, the average position of the local group of stars of which the sun is one, is the reference of rest, the standard of rest, to measure everything else in the galaxy. And so what we have to do when we measure the speed of a hydrogen cloud that's either coming towards us or against or away from us, is we have to know where we are moving. Because if you think about it, 6 months of the year we're moving in one direction around the sun, and the other 6 months we're going in the other direction. Day and night, the Earth is spinning on its axis. And so we have a speed of the ground, of the antenna, that's determined by the Earth's rotation as well. So we've got to figure out what our own motion within this standard of rest is. And it's sort of like, you could reference it to being on a roller coaster. If you're riding on a roller coaster in an amusement park, let's say, and you were given the task of measuring the speed of a train way off in the distance, how would you measure that? What would you measure it against? Well, it turns out that the logical way is to measure it against the amusement park itself, because it's relatively stable, while we're going all around on a roller coaster. So if we can calculate what our instantaneous velocity is on the roller coaster, we can take the vector that's in the direction of what we're trying to measure and subtract that out of the equation, and we get a true speed in relation to this total standard of rest. And that's part of what we have to do with these measurements. And it's really simpler than you think, because thank God there are calculators on the web that you can just plug in the date and the time, and it'll tell you what our VSLR is. Now here's typical. We get down to business here. Here's a typical spectrum capture. This particular one came 80 degrees longitude. And what we see here is we see frequency down here, but it's been corrected into velocity relative to the local standard of rest. I've already done the calculations for the Doppler shift. I've already subtracted out the local motions. And so what we have down here is an actual velocities, positive velocities on this side, negative velocities on this side, and this line is 0, no velocity. And so what we see here is we've got multiple humps. These are Gaussian humps with multiple big clouds in the galaxy. And you can tell by this that this cloud has just got a little bit of negative velocity, so it's pretty much almost running parallel to us. It might be even our local environment, hydrogen in our local environment. And these other two over here have fairly higher negative velocities, and so they are moving away from us. They're receding from us. And if we keep going, this is kind of what we're looking at. We live within a hydrogen cloud here, and we have our telescope that has a certain beam width, and my current telescope is 8 degrees wide. And what you're seeing is individual clumps of hydrogen that have differing Doppler shifts, each one. And it turns out that what we're looking through is arms of the galaxy. Here's an actual video, short video, of what a pass of the Milky Way looks like. Let me show you what we have here. This is the receiver software up here. Again, it's free. You can get this off the internet. Down here, I've got Stellarium running, and it's kind of dim. You don't really see it very well. But this right here is the 8-degree circle that my antenna is basically looking at. And this line here is that's coming across is the axis of the Milky Way. So, and this is the actual spectrum from the receiver over here. Now watch what happens. We're in a part of fairly empty sky here, so there's not a lot going on here. But as the Milky Way comes up and passes through the antenna, like right about now, watch what happens over here. There's your hydrogen signal. You can see different humps, and they actually move slightly in frequency as we pass through the cloud because the structure below it is slightly different than the structure above. And here's the clock showing, that's a real-time clock here showing how long this takes. So this was a capture of about 22 hours, something like that. And to me, that just, I said, okay, this is just the coolest thing I've ever done. So the things to notice from that is that when the Milky Way comes into the antenna's beam, we see the hydrogen signal that at 1420 megahertz rise up about 1 decibel above the noise. And if everything were at rest and not moving, the signal would be a single narrow frequency spike like I showed you earlier. So the fact that the signal appears as humps means that it's being spread in frequency by Doppler shift. And components of each cloud are moving both towards and away from us. And the fact that there are multiple humps separated frequency means that we're seeing multiple hydrogen clouds, each with their own relative radial velocity. So from this simple observation, we can deduce some fairly powerful things. We're surrounded by hydrogen in distinct areas. It's non-uniform. These areas have different relative radial velocities to us. Within each area, the hydrogen is randomly distributed with motions both towards and away from us at a Gaussian frequency distribution. And we see two completely different spectrum patterns approximately 12 hours apart. In other words, looking towards the core and looking away from the core. So our large-scale environment is different in different directions. And as the antennas move in galactic longitude, we see different spectrum patterns, which means that the galaxy is non-uniform in structure. So we're starting to get hints of what the shape is. Now, what I'm doing, I'm running a hydrogen mapping project where I start at the center of the galaxy at 0 degrees longitude and take images or take spectrum shots every 10 degrees of longitude and save those on the spreadsheet. So the easiest thing to do is basically, since my antenna is not motorized, is set up to aim right along the meridian, either the southern or northern. You start with the southern because that's close to the Milky Way. And you calculate using something like Sky or SkyX or Stellarium or something like that. You do a little work calculating where these coordinates are right here. I found this table that gives you the actual celestial coordinate, the coordinates of each latitude at 0 degrees, or excuse me, at each longitude at 0 degrees latitude. And so what I do is I set up the antenna at that position and wait on the Milky Way to pass. It's called the drift scan. So I don't have to trace and track anything like that. I'm basically waiting on the Milky Way to move in front of the antenna. And so this, with the antenna aiming due south or due north, I find the time and the elevation of the galactic equator crossing. It shows the longitude with the planetary software, like I said. I capture the spectrum at the exact time that the equator goes across that meridian, because I want to stay at 0 degrees latitude. And I calculate the observatory velocity relative to the standard of rest using an online calculator, and plug all that data into a spreadsheet for record keeping and to generate these spectrum graphs. And each antenna position will generate 2 galactic longitudes, one looking towards the center and one looking away, 180 degrees apart, about 12 hours apart. So it turns out that doing radio astronomy is not a whole lot different than doing visual astrophotography. They've got a lot of the same common problems inherent in both. For instance, on the picture on the left there, we have to deal with vignetting a lot of times in visual astrophotography because of the restrictive nature of the optical tube and the focuser and all of that stuff. And so we have to take flat frames to subtract or actually to divide into the image frames to get a flat field of view. Likewise, on the right, we see a spectrum from a radio astronomy antenna. And here's the information we're looking for, the hydrogen information, but it's riding on top of this big lumpy thing here that's caused by all the filters in the line, caused by the transmission line, the feed line between the receiver and the antenna, its characteristics and all that. So what we do is we take basically a flat frame of the system and subtract it out, and we end up with a flat spectrum. So but it has a lot of the same issues. And again, the signals are very weak and buried in the noise. So in astrophotography, we don't usually take just a single frame. We stack together. We align and stack many frames because noise averages towards 0 while the correlated signal data is reinforced. And that's how we get these really nice deep space images. You can't do those with just a single frame because they're too noisy. Same thing here. So what I do is I use something called a fast Fourier transform that averages out the signal, and basically I've standardized on 21-second exposures, which basically scans 200,000 times and does a fast Fourier analysis using a 256 bucket data bucket, and I wound up with fairly clean data out of that. Again, the software does all this for free. So let's start looking. Again, I've already gone with this one, so I'm going to skip that. A couple of things before we really get into the data is, our sun orbits around the galaxy, and going on Kepler's laws of motion, anything that's at the same distance from the core as we are would orbit at the same rate. Anything that's closer to the core than we are will orbit at a faster rate, and anything that's farther from the core will orbit at a slower rate, like Jupiter, and it takes how many years for Pluto to go around, that sort of thing. So you can, by looking at the speed that you calculate for each of these hydrogen clouds, you can tell whether it's closer to the core than we are or further out from the core than we are. So that tells you a lot of information there just by doing some deductive reasoning on this. For instance, here's a quick diagram. You see the sun over here. And if we're looking in this direction, if we have our antenna aimed in this direction, here's the core. And we see 1, 2, we actually see a lump here too. We see 1, 2, 3, 4 hydrogen lumps. They're all going to be at different speeds. This one way over here, on the far side of the galaxy, is going to be orbiting at the same speed we are because it's in the same orbit. So it'll have its own right at 0 degree or 0 speed, 0 velocity relative to the standard rest. Anything that's interior to our orbit will be orbiting faster, and the fastest one will always be the one that's tangent to the core. So again, you can use some of this and some geometry and some trigonometry to figure out what the shape of these arms are. This is basically the same thing here. So let's get this. So let's start looking at some actual data. This is with the antenna aimed at 0 degrees galactic longitude. So what we're looking at, here we are right here. We're looking through this arm, which is the Scutum Centaurus arm, and we're looking at the central bar of our galaxy. Our galaxy is just part of a large spiral, by the way. And since all of that is basically running in parallel, there's very little radial motion between those objects, and so everything is pretty much clustered up right around 0 velocity right here. We can tell a little bit of difference. This area right here is traveling slightly slower than we are, and so faster than we are, so it moves over just a little bit. This area right here is traveling slightly slower than we are, so it moves just a little bit that way. But basically, there's very little radial motion when we're looking directly at the core. So let's take a look at the next one. But keep in mind now, as we look at all of this, that we can't see visually much beyond the Orion spur that we inhabit. The Scutum Centaurus arm lying between us and the core pretty much blocks everything. And at longitudes greater than about 45 degrees, we can't see beyond the Perseids arm. So everything on the other side of the galaxy is basically invisible to us. But I can see it with my little radio telescope. Okay, here is, this one is at 28 degrees longitude. I'm just going to skip over the here or there. And what we're looking at, we have a number of humps here. And by using these deductions that we learned earlier, you can basically map them and figure out exactly where the hydrogen clouds are. And matter of fact, this one excites me the most right here, because that is coming from clear on the other side of the galaxy that we can never see visually. I just think that's cool. And as we go further, counterclockwise around the galaxy, we see the shifts in the frequency of the humps. Again, everything on this side is receding, everything on that side is approaching us. As we move further over, look what's happening. Everything at that angle and further out is going to be outside of our orbit, and so all of these humps are going to be on this side, blue shift. What we're seeing here in the middle is just the stuff that's around us in the Orion spur. And again, if we go at an angle like this, we can identify each of these humps with what's on this map. And this is a NASA map. This is supposed to be about the most accurate one that they've come up with. And I hope it is, because I'm seeing exactly what I'm expecting. And you can see even some partial humps and things in here that you can deduce from the thickness of the area and things like that. Now here's where it all comes together. If you map this stuff out, you figure out along each angle, and you figure out where the humps are, how fast they're going, and everything like that, look where it falls out. We're a spiral. This comes from mapping out the data that I just showed you. And this, again, comes from a very simple homemade radio telescope. This is one of the first maps ever done of the galaxy, back in the 1950s, I guess. Now, knowing what I've talked about before, why is there a gap here? Here we are up here. There's a gap directly behind us and a gap directly in front of us, and across on the other side where we can't get any data. Can you figure out why? Remember, all this, we can only see Doppler shifts from things that are either moving away from us or towards us. If it's directly in line with us, remember how when we looked at the core of the galaxy, everything was jammed up around 0? That's the same thing here. You really can't differentiate when you're that close to the center of the galaxy. So there's there's some holes in the maps. Now, just to check what I had come up with, I found this map. This is a map going out at various longitudes out from the core. The core is over there somewhere. Going out from the core. The negative shift, the approaching, is all of this stuff on this side. This is the 0 line. The stuff that's positive and going away from us is on this side. And remember how I said everything that's inside of our orbit is basically outrunning us, is moving faster than we are. If it's like Mercury and Venus outrun us in our journey around the sun, that's what's happening here. When we move out from the center out to about 60 degrees or so, just about everything that you see is moving faster than we are, and receding from us. Once you get out past about 60 degrees longitude, now you start seeing all this stuff down here that's coming towards us, or we're actually coming towards it. So I mapped out all of this and checked all of my readings with it, and it matched perfectly. So I was real happy to see that. And again, all of this together, if the data is collected in a systematic directional study, reveals the spiral structure of our galaxy, even if it can't be seen optically. Taken further, the rotational velocity, the sun's orbital period, and even the mass of our galaxy can be deduced from these simple observations, and all with a small 1.8 meter salvaged antenna and a homemade feed horn and receiver. Now, this is a current project I'm working on with a friend of mine who is much better at data analysis than I am. We're building spreadsheets that can automatically do Gaussian signal analysis to come up with the exact frequencies of all the components that are internal to that curve. The curve is on, the outer curve is all you see from the receiver. But I need to know where the components are, their amplitudes and their shifts, to make up that curve. So he's helping me work out the math to come up with an automated system that can do this. Now this is a pretty neat close-up of the map that I've been using with the galaxy. One thing interesting here, this circle right here we are right here. This circle is the limit of our visibility. Okay? Looking by eyes, these are all the stars that you can see are within that circle. And you can see some of the other arms, which are, of course, combined billions of stars. But every individual star that you can see is right inside of this limit of visibility. So we're going way beyond that with radio astronomy. And one interesting thing, if you really follow up on all of this, you can figure out what the rate of rotation rate of the galaxy is along by its radius. And what you would expect is a curve like this. As we go further out from the center out to the outside, we would expect it to rise up and then fall back down. And that's expected from the visible data, what we can actually see, the mass that we can figure out from what we can see. And that works kind of like our solar system does. The planets, as you further go out, they slow up on an exponential rate. But it turns out that by using radio astronomy to map these rotations, you wind up with a curve like this. And of course, these yellow ones, this is data that was determined from visible stars beyond about 20,000 light years. You can't see them anymore. And so these are radio astronomy observations out here. And what happens is we go up in frequency and it levels off. So there's something different about our galaxy, different from the way the solar system works. And here's let's see if I can get this thing going. I can't get it to work. But anyway, this is an animation that shows, it actually shows the galaxy rotating, and it shows the rotation that you would expect if all we could see is all that there was. Turns out that, here we go, maybe I can get this down here.
It's the Kodak issue on that
This
one.
doesn't play.
Yeah.
What is it, an MOV?
Such is the way of making presentations on one laptop and playing on another. But anyway, so it turns out that there's got to be a lot of extra mass. And it turns out, this is the theory, is that basically the galaxy is encased in a dark matter halo. And again, we found this with a 1.8 meter antenna.
and some calculations. That's pretty cool of it. So the conclusions are, for these systematic measurements, with a homemade radio telescope, we can deduce that we're surrounded by hydrogen in distinct areas, so there's a non-uniform structure around us. These areas have different radial velocities to us. Within each area, the hydrogen is randomly distributed with motions both towards and away from us. We see different spectral patterns as we look at different points along the Milky Way. By plotting the radial velocity with various angles across the Milky Way, a spiral pattern emerges. Moreover, the relative velocities versus distances from the core reveal the presence of an invisible mass, which is now theorized to be dark matter. At that point, I'm going to call it quits because I've got a little bit more, but it doesn't have anything to do with this, and we're running late on time. But do we have any quick questions? Anybody else?